Welcome to the capacitance unit. In your previous studies, you learned how resistors dissipate energy in steady-state circuits. Now, we are going to explore a completely different component, one that stores energy. Capacitors are fundamental to modern electronics. They hold electrical energy physically within an electric field. Unlike a battery, which releases energy slowly through chemical reactions, a capacitor can discharge its stored energy in a fraction of a second. This unit bridges your knowledge of static electric fields and direct current. It moves you into dynamic circuits where potential difference, charge, and current change exponentially over time. In Cambridge Paper 4 and Paper 5, mastering this transition from static circuits to dynamic circuits is a major discriminator for top grades. We begin the unit by defining exactly what a capacitor is, how it is constructed, and how we measure its ability to store charge. Capacitance is defined as the charge stored per unit potential difference. You will learn how the physical geometry of parallel plates dictates this storage capacity. We will also explore why inserting an insulating material known as a dielectric significantly enhances a capacitor's performance. You will see why the farad is actually a surprisingly massive unit of measurement. Next, we will calculate the precise amount of electrical potential energy held within that electric field. Because potential difference is directly proportional to charge, the energy stored is the area under a voltage-charge graph. This triangular area gives us a crucial factor of 1/2 in our equations. You will use these formulas to solve Paper 4 problems on rapid-release energy stores, like medical defibrillators, particle accelerators, and camera flashes.
Once you understand the properties of a single capacitor, we will combine multiple components into complex circuits. Here is a vital exam strategy to lock in early. You must invert your resistor logic. Capacitors in parallel add together directly to increase total capacitance, while capacitors in series use the reciprocal rule. You will use these rules alongside Kirchhoff's laws to break down complex networks. You will learn to find the exact charge distribution and potential difference across any individual component in a circuit.
Finally, we reach the mathematical heart of the unit, charging and discharging capacitors and the crucial concept of the time constant. You will sketch and interpret exponential decay curves for charge, current, and voltage. The rate of this decay is governed by the time constant, which is simply resistance multiplied by capacitance. This value dictates the exact timing of everything from intermittent windscreen wipers to medical pacemakers. You must confidently use natural logarithms to rearrange these decay equations, finding exactly how much charge remains at any given second. And remember a classic exam trap. Whether charging or discharging, the current always starts at a maximum and decays exponentially to 0. To conquer capacitance, you need solid algebra and clear physical logic. You will define capacitance and calculate the energy stored in an electric field. You will combine components in series and parallel networks, remembering to invert your resistor logic, and you will model dynamic exponential decay using the time constant and natural logarithms. You have all the tools you need. Let's get started.